Hi boys and girls, this is lecture 8.5. Our review topic today, motion, part 2. Today we're going to discuss relationships between velocity, speed, and acceleration. Speed is the absolute value of velocity. It tells you how fast something is moving without regard to direction of movement. What effect does absolute value have on numbers? As we know, it makes them positive. Absolute value is the distance a number is from zero, regardless of direction. Therefore, that number is always positive. What effect does taking the absolute value of a function have on its graph? Essentially, it will take any part of the function that's below the x-axis and reflect it above. So nothing will be below the x-axis, it will be reflected above the x-axis. Let's examine a few situations and come to some conclusions about the relationship between velocity, speed, and acceleration. In situation 1, here's our velocity graph. At these times, these are the velocities. Since speed is absolute value of velocity, that means we have a speed of 1, then 2, 4, 8, 16. Now let's answer some questions. Is velocity positive or negative in this situation? In this case, all of the velocities are positive. Is it increasing or decreasing? This is referring to the slopes of this graph, and as you can see, they're all positive, therefore velocity is increasing. What about acceleration, positive or negative? Since that is also referring to the slopes of the velocity graph, that means acceleration is positive. Speed, increasing or decreasing. As these numbers are getting larger, we can see that speed is increasing. Now let's look at situation 2. Here's the velocity graph, times and velocities associated with each time. Since speed is the absolute value of velocity, we have 1, 2, 4, 8, 16. Is velocity positive or negative in this situation? All of the values are negative, so negative. Is velocity increasing or decreasing? Now we examine slopes and see they're all negative. Velocity is decreasing. Since those slopes refer to acceleration, is acceleration positive or negative? Negative. What about speed, increasing or decreasing? Look at the speed values. They're increasing. Now let's look at situation 3. Here's our velocity graph. Our times are velocities. Speed is the absolute value of velocity, so we'd have 16, 8, 4, 2, and 1. Is velocity positive or negative? Since all of the velocity values are negative, negative. Is velocity increasing or decreasing? This is referring to slopes. They're all positive, so velocity is increasing, which means acceleration is positive. But let's look at our speed values. They are decreasing. Now let's look at situation 4. Here's the velocity graph. Our times are velocities. Speed is the absolute value of velocity, so we have 16, 8, 4, 2, 1. Velocity positive or negative? Notice they're all positive values. Increasing or decreasing? Again, this refers to slopes and they are negative. So this velocity graph is decreasing, which means acceleration is negative. Speed, 16, 8, 4, 2, 1, decreasing. All right, we're going to use those 4 situations to draw some conclusions regarding the relationship between velocity, speed, and acceleration. If velocity is positive and decreasing, then speed is, that was situation 4. Velocity positive and decreasing, speed was decreasing. If speed is increasing and acceleration negative, what was velocity? That was situation 2. Speed increasing, acceleration negative, velocity was negative. If velocity is positive and speed is decreasing, what was acceleration? That was situation 4. Velocity positive, speed decreasing, acceleration is negative. If velocity is negative and increasing, then speed is, that was situation 3. Velocity negative, increasing, speed was decreasing. If velocity is negative and acceleration is positive, then speed is, that was also 3. Velocity negative, acceleration positive, speed was decreasing. If the particle is moving to the left and speed is decreasing, then acceleration is, particle moving to the left means velocity is negative, and that was situation 3. Velocity negative, speed decreasing, then acceleration positive. In which situations was the speed increasing? Let's see. In situations 3 and 4, speed was decreasing. In situations 1 and 2, speed was increasing, specifically when velocity was positive and acceleration was positive, or when velocity was negative and acceleration was negative. So our answer, in situations 1 and 2, or when velocity and acceleration positive, or velocity and acceleration negative. When the speed is increasing, then, the velocity and acceleration have same signs. In which situations was the speed decreasing? That was in situations 3 and 4, specifically when velocity was negative and acceleration positive, or when velocity was positive and acceleration negative. So 3 and 4, when velocity was positive and acceleration negative, or when velocity was negative and acceleration positive. When the speed is decreasing, then, the velocity and acceleration have opposite signs. Some concluding thoughts. Speed is the absolute value of velocity. We discovered that if velocity and acceleration have the same sign, both positive or both negative, then speed is increasing. If the velocity and acceleration are opposite in sign, one is positive and the other is negative, then speed is decreasing. There are 3 ways to use an integral in the study of motion that are easily confused, so watch out. The integral of the velocity function v of t dt is an indefinite integral. It will give you an expression for position at time t. Don't forget that you will have a plus c, or constant of integration, the value of which can be determined if you know a position value at a particular time. The integral of the velocity function v of t dt from 1 to 2 is a definite integral. So the answer will be a number. The number represents the change in position over the time interval. By the fundamental theorem of calculus, since v of t equals x prime of t, the integral will yield position at time 2 minus position at time 1. This is also known as displacement. The answer can be positive or negative depending upon if the particle lands to the right or left of its original starting position. The integral of the absolute value of the velocity function v of t dt from 1 to 2 is also a definite integral. And so the answer will be a number. The number represents the total distance traveled by the particle over the time interval. The answer should always be positive. The absolute value of the velocity function is the speed function. Essentially, it converts all negative velocities to positive velocities so that you'll get total distance traveled rather than displacement when you integrate. This is a velocity graph of a particle moving along the x-axis for 0 less than or equal to t less than or equal to 11. It consists of a semicircle and 2 line segments. Use the graph and your knowledge of motion to answer the following questions. At what time t, in the interval from 0 to 11, is the speed of the particle the greatest? Well, there's a simple way to answer this question. Let's convert this velocity graph to a speed graph. Notice that what I've done is I've taken the negative velocities and reflected it across the x-axis. Now this part is the speed graph, and now it's easy to see that speed is greatest at time t equals 8. That's when the absolute value of the velocity is greatest. At which of the times t equals 2, t equals 6, or t equals 9 is the acceleration of the particle the greatest? Explain your answer. Remember, acceleration is the slope of the velocity graph. So at t equals 2, we can see the slope is 0, which means acceleration is 0 there. At t equals 6, acceleration will be the slope of this line. Down 6 over 4 is negative 3 halves. At time t equals 9, the acceleration will be the slope of this line. Up 6 over 2, which is 3. So at t equals 9, the acceleration is greatest. Why? Because velocity slope is greatest there. Now, over what time intervals is the particle moving to the left? Explain your answer. The particle is moving to the left when the velocity is negative, and it's negative on the interval from 4 to 10. 4 less than or equal to t less than or equal to 10 is when the particle is moving to the left. Why? Because velocity is negative there. Over what time intervals is the speed of the particle decreasing? Explain your answer. Well, we learned that speed is decreasing when the signs of velocity and acceleration are opposite. So we're looking for areas where velocity is positive and acceleration negative, or velocity negative and acceleration positive. On this interval, we have velocity and acceleration both positive, so speed is increasing here. But from 2 to 4, we have velocity positive and acceleration negative. So that's a place where speed will be decreasing between 2 and 4. Then from 4 to 8, we have velocity negative and acceleration negative. So this is where speed will be increasing. But from 8 to 10, we have velocity negative, acceleration positive. So this is another interval where speed will be decreasing from 8 to 10. And why? Because velocity and acceleration have opposite signs in those intervals. Okay, we're back with our graph, but notice I've included the areas under the curve. 2 pi for the semicircle, negative 18 for the triangle, or positive if we're considering the absolute value, and 3 halves for this triangle. Our first question, find the total distance traveled by the particle over the time interval from 0 to 11. Well, that's going to be the absolute value of all of those distances. So that's going to be 2 pi plus 18 plus 3 halves, which is 2 pi plus 39 over 2. Find the value of the integral of v of t dt from 0 to 11 and explain the meaning of this integral in the context of the problem. Integrating the velocity function will give us net change in position, or displacement. We take the positive and negative areas and combine them. So 2 pi minus 18 plus 3 halves gives us 2 pi minus 33 over 2, displacement, or net change in position. If the initial position of the particle is x of 0 equals 2, find the position of the particle at time t equals 11. So if the position was 2 at time t equals 0, and net change in position, or displacement, was 2 pi minus 33 over 2, we can find out where the particle is at t equals 11 by adding 2 to the net change in position, 2 pi minus 33 over 2. This becomes 2 pi minus 29 over 2. That is the position of the particle at t equals 11 if it was at 2 at time t equals 0. Let's get some practice using our graphing calculator. The rate of change in kilometers per hour of the altitude of a hot air balloon is given by r of t equals t cubed minus 4t squared plus 6 for the time 0 less than or equal to t less than or equal to 4, where t is measured in hours. Assume the balloon is initially at ground level. So if we use the letter h for the altitude of the balloon, then at time 0 the altitude is 0. This is an initial condition which may be useful in later calculations. Here is a graph of the rate function. When the values are positive, the altitude is increasing. When the values are negative, the altitude is decreasing. Use the zero function on your calculator to find where the values change from positive to negative and negative to positive. That's 1.57 and 3.51 hours. So, for what values of t, 0 less than or equal to t less than or equal to 4, is the altitude of the balloon decreasing? That will be where our rate function is negative. So between 1.57 hours and 3.51 hours. Find the value of r prime of 2 and explain the meaning of the answer in the context of the problem. Indicate units of measure. R prime will be the rate of change of our rate function. So let's find the derivative of r of t. R prime of t is 3t squared minus 8t, which means r prime of 2 will be 12 minus 16. Negative 4 kilometers per hour squared. Since the units for our rate function is kilometers per hour, the units for the derivative of the rate function will be kilometers per hour squared. This function is the rate of change of the rate. What is the altitude of the balloon when it is closest to the ground during time interval 2 less than or equal to t less than or equal to 4? Well, let's imagine what the altitude of the balloon is doing. These positive values mean that it's increasing. It continues to increase until it gets to hour 1.57, and then it begins to decrease. Continues to decrease until it gets to hour 3.51, and then begins to increase again. So this is where it's closest to the ground. So we can find the height of the balloon at time 3.51 by adding the height at time 0, which was 0, to the integral of 0 to 3.51 of our rate function, which is t cubed minus 4t squared plus 6 dt. Using your graphing calculator and the integrate function, you'll find that the height at that time was 1.348 kilometers. Find the value of the integral of r of t dt from 0 to 4 and explain the meaning of the answer in the context of the problem. Indicate units of measure. Well, integrating the rate function will give us net change in position, or displacement. Our balloon started at height 0, and 4 hours later, how high from there was it? Remember, on its way to 4 hours, it increased, decreased, and increased again. So if we once again draw what we think was happening with the balloon, increasing until 1.57 hours, decreasing until 3.51 hours, and then increasing for a short time, our interval ends at 4. So what was the net displacement between 0 and wherever it was at 4 hours? That is the value of this integral. We'll use our calculators to integrate and find net change in position. From 0 to 4, t cubed minus 4t squared plus 6 dt is 2.667 kilometers. So at hour 4, our balloon was at 2.667 kilometers. Find the value of the absolute value of r of t dt from 0 to 4 and explain the meaning of the answer in the context of the problem. Indicate units of measure. This integral will give us total vertical distance traveled by the balloon, whether it was traveling up or down. It will add all of that vertical distance together. On our calculators, we'll find that the absolute value of our rate function, t cubed minus 4t squared plus 6 dt, is 11.529 kilometers. What is the maximum altitude of the balloon during the time interval from 0 to 4? Well, the maximum altitude could occur at two places, where we have the maximum value, the rate is changing from positive to negative there, or at the endpoint of the interval. We know that at time 4 hours, it was at 2.667 kilometers. So let's find out where it was at 1.57 hours. Once again, we'll use our initial condition, which was 0, and then add to that the integral from 0 to 1.57 of our rate function, t cubed minus 4t squared plus 6 dt. We find that at hour 1.57, the balloon was at 5.779 kilometers, which is higher than where it was at 4 hours, 2.667 kilometers. So the maximum height achieved by the balloon was 5.779 kilometers. The table below gives values for the velocity and acceleration of a particle moving along the x-axis for selected values of time t. Both velocity and acceleration are differentiable functions of time t. That means they're continuous. The velocity is decreasing for all values of t from 0 to 10. Use the data in the table to answer the questions that follow. Is there a time t when the particle is at rest? And explain your answer. We know the particle is at rest when velocity is 0, and as we look at the velocity values, we don't see a 0 value. However, we do see a place where it changes from positive to negative. Because this is a continuous function, by the intermediate value theorem, we're guaranteed a point between here when the velocity was 0. So we can say yes. That happens somewhere between time t equals 2 and time t equals 6. And the reason for that is velocity changes from positive to negative. At what time indicated in the table is the speed of the particle decreasing? And explain your answer. Well, we learned earlier in this video that speed is decreasing when velocity and acceleration have opposite signs. So notice there's one time in the table where that's occurring at time t equals 2. And so we would say at t equals 2, why? Velocity and acceleration have opposite signs. Use a left Riemann sum to approximate the integral of v of t dt from 0 to 10. Show the computations you use to arrive at your answer. Explain the meaning of the definite integral in the context of the problem. We know that the integral of the velocity function will give us net change in position, or displacement. The Riemann sum will give us an approximation of that value. Notice I have sketched the Riemann sum here. Here are the velocity values, 5, 3, -1, -8, and using the left endpoint of each interval, I've constructed a rectangle. Let's find the areas of these rectangles and add them up to get the approximation of the integral. The width of the first rectangle is 2, so it'll be 2 times 5. The second rectangle has a width of 4, 4 times 3. And the third rectangle has a width of 4, 4 times -1. That's going to be 10 plus 12 minus 4, which is 18. So an approximation of the net displacement of this particle is 18. Is the approximation found in part 3 greater than or less than the actual value of the definite integral shown below? Explain your reasoning. The approximation we found is going to be greater than the actual value of this definite integral because the velocity function is decreasing and we used a left endpoint Riemann sum. The rectangles that we constructed were over approximations of the area under the curve. Approximate the value of the absolute value of v of t dt from 0 to 10 using a trapezoidal approximation with 3 subintervals indicated by the values in the table. Show the computations you use to arrive at your answer and explain the meaning of the definite integral in the context of the problem. The pink lines represent the trapezoidal approximation. I've taken the negative velocity values and made them positive, and when we add up the areas of these 3 trapezoids, we'll have the approximation of this integral. This integral will find the total distance traveled by the particle. Remember that the area of a trapezoid is 1/2 times the height times the sum of the bases. So for the first trapezoid, we have a width or height of 2. So this will be 1/2 times 2, the sum of these bases, 5 plus 3. Then the width of the second trapezoid is 4, and the bases are 3 and 1. The width of the third trapezoid is 4, the bases 1 and 8. So this will be 16 plus 16 plus 36, and then we'll take half of that sum. That's going to be 34. This is an approximation of the total distance traveled by the particle. Determine the value of the integral of a of t dt from 0 to 10. Explain the meaning of the definite integral in the context of the problem. This integral will find net change in velocity, and since we know what beginning and ending velocity are, we can find the value of this integral. We'll need to find v of 10 minus v of 0. That was -8 minus 5, which is -13. For our last example, we have a free response question from the 2010 AP exam. No calculator is allowed for this problem. A squirrel starts at building A at time t equals 0 and travels along a straight horizontal wire connected to building B. For 0 less than or equal to t less than or equal to 18, the squirrel's velocity is modeled by the piecewise linear function defined by the graph above. In the interest of time, I went ahead and calculated the areas under the curve, which, as we know, represents distance traveled by the squirrel. At what times in the interval 0 less than t less than 18, if any, does the squirrel change direction, and give a reason for your answer? We know that the squirrel changes direction when the velocity changes from positive to negative or from negative to positive, and that happens twice in this interval, at t equals 9 and at t equals 15. So that's our answer, t equals 9 and t equals 15. Why? Because velocity changes signs. Letter B states, at what time in the interval 0 less than or equal to t less than or equal to 18 is the squirrel farthest from building A, and how far from building A is the squirrel at that time? Let's use these areas to determine the squirrel's position from the building. At time t equals 9, the squirrel was at position 140. But then he changed directions and went 50 units to the left. So at time t equals 15, the squirrel was at position 90. Then he changed directions again and went 25 units to the right. So at time t equals 18, he was at position 115. Therefore, at time t equals 9, he was furthest from the building. So that's our answer. At time t equals 9, how far from the building? 140. Now let's find the total distance the squirrel travels during the time interval 0 less than or equal to t less than or equal to 18. That's just the absolute value of all of these areas. So that's going to be 140 plus 50 plus 25, which is going to be 215. Write expressions for the squirrel's acceleration a of t, velocity v of t, and distance x of t from building A that are valid for the time interval 7 less than t less than 10. Acceleration is just going to be the slope of this line from time t equals 7 to time t equals 10. That can be calculated by taking -10 minus 20 over 10 minus 7. That's -30 over 3, which is -10. That's a of t. The velocity function will be the equation of this line. We know the slope, so with that value and one of the points, we can write the equation of this line. V minus 20 is equal to -10 times t minus 7. Let's distribute the negative t. V minus 20 is equal to -10t plus 70, which means v of t, our velocity function, is -10t plus 90. To find the position function, we're going to need to integrate this velocity function. We'll also need to know the position of the squirrel at time t equals 7. So let's find the area of this trapezoid. That area is 120. That means at t equals 7, the squirrel was at position 120. So when we set up our position function, we have to say 120 plus the integral from 7 to some x value in the interval from 7 to 10 of our velocity function, negative 10t plus 90 dt. When we integrate, we'll have x of t equals 120 plus negative 5t squared plus 90t evaluated from 7 to x. X of t is equal to 120 plus negative 5x squared plus 90x minus negative 5 times 7 squared plus 90 times 7. In the interest of time, this simplifies to x of t equals negative 5t squared plus 90t minus 265. And that's your position expression. Here are the scoring guidelines for that question. For letter A, 1 point for the t values, 9 and 15, and 1 for the explanation. For letter B, 1 point for identifying the candidates, 0, 9, 15, and 18, at which the squirrel could have been farthest from the building, and 1 point for the correct answers. For letter C, 1 point for the answer. For letter D, 1 point each for A of t, V of t, and X of t. Tip number 5 for the AP Calculus AB exam. Do not waste time erasing bad solutions. If you change your mind, simply cross out the bad solution after you have written the good one. Crossed out work will not be graded. If you have no better solution, leave the old one there. It might be worth a point or two. Common student error number 5. Graders will assume the correct antecedents for all pronouns used in justifications. Translation: avoid using the word it. Be specific in your descriptions. That's it for today's lecture. When all else fails, just do it. God bless you, boys and girls.